Have you ever looked up at the night sky and felt a sense of wonder? The universe is a vast and mysterious place, full of secrets waiting to be uncovered. For centuries, scientists have been on a quest to unravel these mysteries. One of the biggest questions that has puzzled physicists is how to reconcile our two best theories of physics, general relativity and quantum mechanics. General relativity, developed by Albert Einstein, explains the behavior of very large objects, like stars and galaxies. Quantum mechanics governs the realm of the very small, the world of atoms and subatomic particles. This conflict has been a major headache for physicists, leading to a search for a theory that could unite these two pillars of modern physics. Enter string theory, a revolutionary idea that has the potential to change everything we thought we knew about the universe. String theory starts with a simple yet radical premise. What if the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings? In string theory, these different vibrations correspond to different particles and forces. It suggests that all the particles we know, electrons, quarks, photons, are just different notes played on these cosmic strings. This is the ultimate dream of physicists, a theory of everything. Imagine the universe as a grand, intricate dance floor. On this dance floor, countless particles are swirling, twirling, and interacting in a delicate balance governed by a set of elegant rules. These rules, the laws of physics, dictate how these particles move, interact, and form the structures we observe in the cosmos. General relativity, developed by Albert Einstein, takes center stage when it comes to the grand waltz of planets, stars, and galaxies. It paints a picture of gravity not as a force pulling objects together, but as a curvature in the very fabric of space-time. Just as a skilled dancer glides effortlessly across the ballroom floor, massive objects like stars and planets create graceful curves in the fabric of space-time, influencing the paths of other celestial objects around them. This curvature of space-time is what we perceive as gravity. General relativity has been incredibly successful in explaining the motions of planets, the bending of light around massive objects, and even the evolution of the universe itself. Quantum mechanics, on the other hand, takes us on a whirlwind tour of the microscopic world, a realm where particles behave in ways that often defy our everyday intuition. Instead of well-defined positions and trajectories, particles in the quantum realm exist in a haze of possibilities. For much of the 20th century, these two theories coexisted, each reigning supreme in their respective domains. General relativity described the grand cosmic ballet of stars and galaxies, while quantum mechanics illuminated the intricate dance of subatomic particles. Yet, despite their successes, a fundamental tension lingered between them. The very fabric of space-time, smooth and continuous according to general relativity, becomes a turbulent sea of quantum fluctuations at the smallest scales. This clash of titans has puzzled physicists for decades, leading to a relentless search for a more fundamental theory. Imagine a world where the fundamental building blocks of matter are not tiny, indivisible particles but rather minuscule, vibrating strings of energy. These strings, far smaller than anything we can currently observe, are the heart of string theory, a radical yet elegant attempt to unify the laws of physics. Each vibration, each note on this cosmic string, corresponds to a different particle. Instead of a vast and seemingly arbitrary collection of fundamental particles, string theory proposes a universe built from a single fundamental entity, the vibrating string. These strings are so incredibly small, billions of times smaller than an atom, that they appear as point-like particles to us. Now imagine a whole symphony of these strings, each vibrating at different frequencies, interacting and intertwining to create the tapestry of the cosmos. Some strings might vibrate in ways that produce the familiar particles we know and love: electrons, quarks, photons. This symphony of strings, with its intricate harmonies and resonances, could hold the key to unifying the seemingly disparate forces of nature. In string theory, gravity is carried by a specific type of vibration, a particular note played on these cosmic strings. Similarly, the electromagnetic force, the strong nuclear force, and the weak nuclear force all arise from different vibrational patterns of these fundamental strings. String theory offers an elegant solution to one of the biggest puzzles in modern physics, the incompatibility between general relativity and quantum mechanics. String theory steps in as a skilled choreographer, guiding these two forces into a harmonious dance. Their extended nature, unlike the point-like nature of particles, smooths out the turbulent quantum fluctuations that plague general relativity at extremely small scales. Imagine trying to balance a basketball on the tip of your finger, a nearly impossible feat. Similarly, the extended nature of strings helps to tame the wild quantum fluctuations, providing a more stable and consistent framework for incorporating gravity into the quantum world. But the elegance of string theory comes with a price. To accommodate these vibrating strings and their intricate dance, physicists had to expand their view of the universe itself. String theory, it turns out, requires more than the three spatial dimensions we experience in our everyday lives. Instead of just length, width, and height, string theory suggests that the universe has additional hidden dimensions tightly curled up and invisible to our current technology. These extra dimensions hidden from our view could hold the key to understanding the true nature of strings and their vibrations. Imagine a world beyond our perception, a realm of extra dimensions hidden from our everyday experience. Think of a garden hose stretched across a garden. From a distance, it appears as a one-dimensional line. But zoom in closer, and you'll notice a second dimension, the circular dimension around the hose itself. String theory suggests that our universe may be structured in a similar way. These extra dimensions, instead of stretching out to infinity like the dimensions we experience, are curled up at incredibly small scales, billions of times smaller than an atom. You might wonder, if these extra dimensions are hidden from view, how could we ever hope to detect them? How can we be sure they're even there? One way to picture these hidden dimensions is to imagine a tightrope walker moving along a thin cable. From far away, the tightrope walker appears to move only back and forth along a single line. But zoom in closer, and you'll see that the tightrope walker can also move around the cable's circumference, a dimension hidden from view at a distance. Similarly, string theory proposes that our universe, while appearing three-dimensional to us, might have additional dimensions curled up at incredibly small scales. The existence of these extra dimensions might seem like a mind-boggling concept, and it certainly pushes the boundaries of our imagination, but it's a concept that emerges naturally from the mathematics of string theory. In fact, string theory doesn't just suggest the possibility of extra dimensions, it requires them. The mathematics of string theory only works if the universe has more than the three spatial dimensions we experience daily. The most popular version, known as superstring theory, requires a total of 10 dimensions, 9 spatial dimensions and 1 dimension of time. Now you might be wondering, what do these extra dimensions have to do with the real world? How do they affect our everyday lives? The shape and size of these extra dimensions, how they are curled up and compactified, could have a profound impact on the physics we observe in our three-dimensional world. Imagine a garden hose again. This time, imagine that the hose is not perfectly smooth but has a series of ridges and grooves running along its length. Similarly, the precise geometry of the extra dimensions in string theory could influence the properties of particles and forces in our three-dimensional world. In a sense, these hidden dimensions could be the unseen architects of our reality, shaping the fundamental properties of the universe from a realm beyond our direct perception. The universe, in all its grandeur and complexity, often reveals itself through patterns, through symmetries that hint at underlying order and elegance. In the quest to unravel the deepest secrets of the cosmos, physicists have often turned to the concept of symmetry as a guiding principle, a beacon illuminating the path towards a more complete understanding of the universe's fundamental laws. Symmetry, in its essence, reflects a sense of balance and harmony. It's the idea that something remains unchanged when subjected to a particular transformation. Think of a perfect snowflake, its delicate structure unchanged when rotated by 60 degrees. Or consider a mirror image, a reflection that preserves the object's form while reversing its orientation. In the realm of physics, symmetry plays a crucial role in shaping the laws of nature. It dictates how particles interact, how forces behave, and how the very fabric of spacetime is structured. The standard model of particle physics, our current best description of the subatomic world, is built upon a foundation of symmetries, with different symmetries giving rise to the fundamental forces and particles that make up our universe. Yet even as the standard model has achieved remarkable success in explaining a wide range of phenomena, it leaves some profound questions unanswered. It doesn't incorporate gravity, and it doesn't explain the masses of neutrinos or the existence of dark matter and dark energy. These mysteries hint at a deeper layer of reality, a realm where new symmetries might be waiting to be discovered. Enter supersymmetry, a bold and elegant extension of the standard model that proposes a fundamental symmetry between matter particles, the building blocks of everyday objects, and force particles, the carriers of fundamental interactions. It's a concept that has captivated physicists for decades, offering the tantalizing possibility of resolving some of the most perplexing puzzles in modern physics. Imagine a grand cosmic dance floor where every particle we know and love has a secret twin, a supersymmetric partner with slightly different properties. For every electron, a selectron; for every quark, a squark; for every photon, a photino. These superpartners, predicted by supersymmetry, would complete the particle family portrait, introducing a new cast of characters to the quantum world. But these superpartners wouldn't just be mere copies of their standard model counterparts. They would possess a crucial difference: their spin. Spin, a fundamental property of particles, is a bit like their intrinsic angular momentum, a measure of how much they rotate. In the quantum world, spin is quantized, meaning it can only take on specific, discrete values. Supersymmetry postulates that every known particle with half-integer spin, like electrons and quarks, has a superpartner with integer spin, like the force-carrying particles, and conversely, every known particle with integer spin has a superpartner with half-integer spin. It's a beautiful and symmetrical concept, linking matter and forces in a profound way. This symmetry between matter and force particles has profound implications for our understanding of the universe. For one thing, it could help to solve the hierarchy problem, a puzzle related to the vast difference in strength between the weak force responsible for radioactive decay and gravity, the weakest of the fundamental forces. Supersymmetry could provide a candidate for dark matter, the elusive substance that makes up a significant portion of the universe's mass. Some supersymmetric particles could fit the bill, offering a possible solution to one of cosmology's biggest mysteries. Physicists search for evidence at high-energy particle accelerators, hoping to glimpse these elusive partners in the quantum dance. In string theory, strings might not be the only actors. Imagine a universe with higher dimensional objects called branes. These branes, like cosmic sheets, add complexity to reality. Branes can vibrate, potentially creating entire universes. Our universe could be a three-dimensional brane in higher dimensional space. M-theory unifies string theory, revealing a universe far stranger than imagined. Our universe might be confined to a brane, a cosmic island in a higher dimensional sea. This could explain why we experience only 4 dimensions while others remain hidden. Imagine ants on a sheet of paper. To them, their world is flat. They are unaware of the 3rd dimension. Similarly, we might be oblivious to extra dimensions beyond our brain. These dimensions could still have observable effects. Just as Earth's curvature affects airplanes, higher dimensional branes could influence gravity. Some physicists propose dark energy might result from nearby branes' gravitational pull. The fabric of reality unveiled, M-theory, with its tapestry of branes woven through higher dimensional spacetime, offers a captivating vision of reality. The sheer mathematical complexity is a major hurdle. Another challenge is the lack of experimental evidence. M-theory predicts extra dimensions and microscopic black holes. It suggests our universe might be one of many. The quest to understand M-theory is a testament to our relentless drive to explore the unknown. The rewards could lead us to a unified theory of physics. A tapestry of universes. Imagine a universe where the Big Bang is a common event, a cosmic symphony of creation echoing throughout the multiverse. M-theory suggests brain collisions in higher dimensional space could trigger new universes. Picture two giant sheets colliding, releasing energy, igniting a new Big Bang. A baby universe expands and evolves within the higher dimensional space. This process could be happening all the time throughout the multiverse, a realm teeming with diverse universes, each with unique physical laws. Section 1. The future of physics. String theory promises to unify the laws of physics and reveal hidden dimensions of reality. It's a grand tapestry woven from intricate mathematical threads, but some threads are still missing. The lack of experimental evidence and mathematical complexity pose significant challenges. Yet the allure of string theory remains strong, promising a deeper understanding of the universe. If correct, it would revolutionize our understanding of space, time, and the cosmos. The quest to understand string theory is a journey into the unknown, driven by curiosity and wonder.